Light travels in straight lines. Everyone knows this. Shadows have sharp edges. Laser pointers make straight beams. You look at a star and draw a straight line to your eye. But what is a straight line? How do you know light is taking the straightest path? What if space itself isn't straight? What does straight even mean when nothing is there to measure against? People say light travels in straight lines, but that's just describing what we see from our perspective, not explaining what light is doing or why. The truth is stranger. Light is always taking the straightest path. It's space that isn't straight. The reason has nothing to do with light being attracted. It's about what straightness means when geometry itself can curve. Everyone says gravity bends light. But what does that even mean? Gravity pulls on things with mass. Light has no mass. Well, no rest mass. So how does gravity pull on something massless? You hear photons are affected by gravity, but that's just restating the question with fancier words. It doesn't explain anything. What if we're asking the wrong question entirely? Imagine you're in an elevator. The cables snap. You fall. While falling, you drop your keys. They float beside you. Not because gravity disappeared, because you're both falling at the same rate. You can't tell the difference between floating in deep space and falling in that elevator, assuming you have no windows to look out of. Einstein said, "This realization was the happiest thought of my life." He saw something in it. What? When you stand on Earth, you feel weight. In a certain sense, Earth's surface is accelerating upward into you. Free fall. That's the natural motion. No forces. Gravity is what you feel when something, the ground, interrupts that free fall. Well, not exactly interrupts. That's not quite right. When you're in free fall, there is no gravity in your local experience. You're weightless, like the astronauts on the space station. They're falling continuously around Earth, never hitting it. From their perspective, no gravity at all. But wait, if free fall is natural motion with no forces acting, what path does it follow? Draw a straight line on paper. Easy. But what about on Earth's surface between two distant cities? An airplane doesn't fly straight in three-dimensional space. It follows a great circle, which curves over the globe. That's the straightest path on a curved surface, the shortest distance between 2 points given the geometry you're working with. We call this a geodesic. On flat paper, a geodesic is a straight line. On a sphere, it's an arc of a great circle. Here's the key insight. What counts as straight depends entirely on the geometry of the space you're in. Ships sailing straight across the ocean actually follow Earth's curve. From space, their path curves. From their perspective on the surface, they're going perfectly straight. They're not turning their wheel. They're following the natural path that the curved surface offers. So here's the thing about light. Light has no choice in the matter. It always takes the shortest path through space-time, always follows a geodesic, the straightest possible route. Now suppose you're in that falling elevator again. You shine a laser pointer across the elevator. From your perspective, falling with the elevator, the beam goes perfectly straight across. From an outside observer watching the elevator fall, the beam curves downward, following the elevator's fall. Both perspectives are correct. Different viewpoints, different descriptions, same reality. But here's what changes everything. Massive objects don't just sit in space. They change the geometry. Actually, that's not quite right. They don't change the geometry as if it was there first. They are the geometry change. The sun doesn't pull on light passing nearby. The sun curves space-time around itself. Light passing by simply follows the new geodesic through that curved space-time. Let me prove it to you. Einstein predicted this in 1915. Light from distant stars passing near the sun should bend. The amount would depend on exactly how much the sun curves space-time. But there was a problem. You can't see stars near the sun in daytime. The sun is far too bright. The solution? A total solar eclipse. May 29th, 1919. Arthur Eddington traveled to an island off the coast of Africa. During the eclipse, he photographed stars near the sun's edge. Months later, he photographed the same stars at night when the sun was nowhere near them. The stars appeared shifted during the eclipse, exactly the amount Einstein had predicted. 1.75 arcseconds of deflection. The news made front pages worldwide, lights all askew in the heavens. Newton's theory actually predicted bending too, treating light as particles with tiny mass, but it gave the wrong amount, half of Einstein's value. The observation matched Einstein's prediction. Not approximately, exactly within the limits of measurement. Which means what, exactly? Space isn't just an empty stage where events happen. It's a dynamic, flexible, geometric structure. Mass tells space how to curve. Space tells mass how to move along geodesics. You've probably seen the image of the sun sitting in space like a bowling ball on a trampoline making a dip. But actually, that metaphor is misleading. It suggests there's some external gravity pulling the ball down into the trampoline. Better to imagine three-dimensional space itself having intrinsic curvature. An ant walking on the surface of a balloon doesn't need a third dimension to experience the balloon's curvature. The curvature is a property of the surface itself, something you can measure without ever leaving that surface. GPS satellites prove this every day. The satellites orbit Earth in weaker gravity, farther from Earth's center. Time runs faster up there, a few microseconds per day faster, because space-time is less curved up there. GPS systems must correct for this difference, or else your position would drift kilometers per day. This is an engineering fact, not some theoretical curiosity. Your phone's GPS works because we account for space-time curvature in the calculations. But where does the curvature come from? Not just mass, any energy. Einstein's EMC2 tells us that mass is concentrated energy. Light carries energy even though it has no mass. So in principle, a light beam should curve space-time too, just an incredibly tiny amount. The sun curves space-time because it has enormous energy content. Even Earth curves it, less dramatically. You curve it infinitesimally. Everything with energy curves the geometry around it. Black holes are the extreme case. So much energy and mass concentrated in such a small region that space-time curves back on itself. Geodesics near a black hole spiral inward. Light tries to go straight, but the straightest path available leads inward. The event horizon marks the boundary, where geodesics stop leading outward at all. Not because something is pulling the light in, because the geometry simply doesn't provide any outward paths anymore. All the straight lines point toward the center. Think about what this means for everything. The universe isn't objects moving through space. It's space-time geometry being shaped by what's in it. Gravity isn't a force in the usual sense, like pushing or pulling. It's curvature. When you fall, no force acts on you. You're following the natural path through curved geometry. When you stand on the ground, The ground does exert a force on you, pushing upward. That's what you feel as your weight. The gravity paradox gets reversed. We don't feel gravity when we're falling freely. We feel the absence of gravity, what we call weight, when something prevents the free fall. An upward force, the ground pushing on your feet, your chair pushing on you right now. This changes cosmology fundamentally. The universe can expand, not objects moving apart through fixed space, but the geometry itself growing, space between objects increasing. Distant galaxies appear to be receding faster than light, but they're not violating the speed limit. They're not moving through space. Space itself is expanding between us and them. Light from the early universe gets stretched by this expansion, red-shifted. All of modern astronomy depends on understanding space-time geometry. And stranger still, you can't curve just space. You must curve space-time. Time and space are inseparable, different aspects of the same geometric structure. Time runs at different rates depending on gravitational potential. Deeper in a gravity well means slower time. This is measurable. This is proven. This is an engineering fact. Your head ages slightly faster than your feet. An infinitesimal amount? Yes, but real. High-precision atomic clocks can detect this difference over just 1 meter of height. Time itself is geometric. The duration between events depends on the path you take through space-time, just like distance depends on the path you take across a curved surface. Two people taking different paths through space-time between the same two events will experience different amounts of elapsed time. Both are correct. Time isn't absolute. It's woven into the fabric of geometry. Which raises the next question. So light does travel in straight lines, the straightest lines possible. It's just that straight means something different when geometry curves. The sun doesn't grab photons and bend their paths. The sun bends the geometry. Light follows that geometry. From the light's perspective, it's going perfectly straight the entire time. From our perspective far away, watching, the path curves. Both descriptions are true simultaneously. But why does energy curve space-time? What is space-time that it can be curved in the first place? Einstein's equations describe how mass-energy curves geometry. They work perfectly. The mathematics is beautiful. We can predict GPS corrections, gravitational waves, black hole shadows, the whole expanding universe. But why this connection exists between energy and geometry, that's a different kind of question. I've got to stop somewhere. The mathematics works. The universe operates this way. We've tested it to extraordinary precision. But the ultimate why, that remains mysterious.